Have you ever stopped to think about what really makes our modern world work? You know, it's not just the software in our phones or the gas in our cars. It's the materials, the hidden, unsung heroes of engineering that make everything, from massive airplanes to tiny little electronics, even possible. So today we're going to pull back the curtain on these amazing materials, and we're starting with one of the most demanding places you could ever imagine.
Okay, just look at this thing. It's a modern jet engine. I mean, we see a 70-ton airplane just lift off into the sky, and we think about aerodynamics, we think about thrust, but what really lets this incredible machine defy gravity is the stuff it's made of. It's literally an orchestra of metals inside, with each one playing a totally critical part.
And you know, if you actually break down its composition, you find something really surprising. There's almost no iron in sight. A jet engine is basically a treasure chest of what we call non-ferrous metals. A whopping 38% is titanium, and another 37% is nickel. Then you've got chromium, cobalt, and aluminum filling in the rest. And every single one is there for a very specific, very high-stakes reason.
So let's dive in and take a closer look at what these metals are actually doing inside that engine. Because each one kind of has its own personality, its own special job to do, and when they all work together, well, it's just pure engineering magic.
The best way to think about it is to give them personalities. So titanium? That's the athlete. It's incredibly strong, but also super lightweight. And that high strength-to-weight ratio is absolutely perfect for those giant fan blades you see at the front, and for the compressors that are squeezing the air. Then you've got the nickel superalloys. These are the firefighters. They can handle just insane temperatures, which makes them absolutely essential for the hottest parts of the engine, like the combustion chamber and the turbine blades.
So, seeing these incredible properties brings up a pretty big question. If regular old steel is so strong and, cheap, why even bother with all these other exotic, expensive metals? Well, as you're about to see, it all comes down to a fundamental trade-off in engineering. You're always balancing amazing performance against a pretty hefty price tag.
First off, what are we even talking about here? A non-ferrous metal is, quite simply, any metal or alloy that doesn't have a significant amount of iron in it. So, instead of the properties you get with steel, you get this whole different menu of options to choose from. Things like being super lightweight, fantastic at conducting heat and electricity, and amazing resistance to rust and corrosion.
But yeah, that performance comes at a very steep price. This slide really gives you that sticker shock moment. If we set the cost of basic carbon steel at 1, aluminum alloys are already up to 3 times more expensive. But just look at our jet engine stars. Titanium is 25 to 40 times the cost, and nickel is right there with it. It just goes to show you, you only use these special metals when you have absolutely no other choice.
And that need for lightweight strength? It isn't just up in the sky. It's right here on our streets, where the very same engineering principles are totally changing the cars we drive, especially now with the rise of electric vehicles.
We all know the Tesla Model S, right? But if we had X-ray vision, we'd see what really makes it work. That slick body isn't just for show. It's built on a lightweight aluminum frame and body panels. And that was a very deliberate choice to solve a really massive engineering challenge.
And here is that challenge in one number: 455 kilograms. That's how much the battery pack alone weighs. I mean, think about that. To get any kind of decent performance or range with that much weight just sitting there, the rest of the car has to be as light as humanly possible. Aluminum is the secret sauce that makes that happen.
So where does this lightweight wonder metal even come from? Well, it all starts as this reddish rock called bauxite. Now, to unlock the aluminum inside, the ore is first crushed up and heated to produce this refined white powder called alumina. But the aluminum is still chemically locked away. To finally break it free, that powder is dissolved, and then a massive electrical current is zapped through the solution, separating out the pure, molten aluminum. This right here is the heart of that process. It's called the Hall-Héroult reduction pod. And when we say it's energy intensive, that is a serious understatement. To put it into perspective, it's estimated that producing aluminum this way uses up about 5% of all the electricity generated in the entire United States. That's a staggering amount of power, just to turn rock into the metal we use for our cars and soda cans.
And this story doesn't even end with the frame. The lightest metal of them all, lithium, is actually playing a double role here. It's obviously the key ingredient in the car's batteries, but now engineers are mixing it into aluminum to create brand new alloys that are even stronger and lighter than before.
All right, so beyond the high-flying champs like titanium and the lightweight workhorse aluminum,
there's this whole other world of non-ferrous metals doing critical jobs all around us. So let's do a quick tour of a few other key players you might not even think about.
First up, copper. Look, if our modern world runs on electricity, then copper is its backbone. Simple as that. It's one of the best conductors out there, which is why it's in pretty much every wire and electronic device you own. And, of course, when you mix it with zinc, you get brass, or with tin, you get bronze, two alloys that we've been using for literally thousands of years.
Next up, zinc, who I like to call the great protector. Its main job is in a process called galvanizing. You basically coat steel with a thin layer of zinc, and it creates this shield against rust. What's so clever about it is that the zinc is more reactive, so it actually corrodes first, sacrificing itself to protect the steel underneath. Pretty smart, right?
Okay, so we've seen strong metals, light metals, conductive metals, but material science never ever stands still. So what's next? Well, the future lies with smart materials, metals that almost seem to have superpowers.
Let me just ask you a question. What if a metal could have a memory? I mean, what if you could bend it, twist it, even tie it in a knot? And then, with just a little bit of heat, have it snap right back to its original shape?
Well, that's not science fiction. These are real. They're called shape memory alloys, or just smart materials. An alloy like nitinol, which is a mix of nickel and titanium, can be programmed with a specific shape. You deform it, apply a little heat, and bam, it snaps right back. This is being used for everything from tiny actuators in spacecraft to medical stents that open up inside an artery once they warm up to your body temperature.
And check out this beautiful, bizarre structure. This is metal foam. It's mostly empty space, we're talking up to 95% air, with a metal web supporting it. This gives it this unbelievable combination of lightness and strength. People are exploring it for ultralight aerospace parts and even orthopedic implants, where its spongy structure can actually encourage your own bone to grow right into it.
And finally, let's bring it right into your own pocket. The term rare earth metals sounds super exotic, but these things are absolutely essential to the tech we use every single day. Those tiny but incredibly powerful magnets in your headphones, that's neodymium. The bright, vibrant colors on your phone screen, yttrium helps make that possible. And that high-performance battery in a hybrid car, yep, that needs lanthanum.
And this actually brings up a really common misconception. They aren't called rare earths because they're, geologically rare. Some are actually more common than lead or silver. No, they're called that because they are just incredibly difficult and messy to mine and separate into their pure forms. When you really think about it, the story of human progress is the story of materials. From the Stone Age to the Iron Age to today, the materials we can master have always defined the absolute limits of what we can build. So looking at things like smart alloys and metal foams, it really makes you wonder, what incredible new technologies will this next generation of materials unlock for us? And what will that future even look like?